Hello, and welcome to today's webinar, New Generation GNSS Solutions, Precise Positioning, Navigation, and Applications. This is brought to you by our sponsor, Hemisphere. I'm Bethany Chambers from North Coast Media, publisher of GPS World Magazine, and I will be your event manager. Before we begin, I'm going to go over some ways that you can participate during today's presentation. Although you are currently in a listen-only mode, we encourage you to ask questions throughout the presentation. Just type in the text box at the bottom left, then click Submit to place your question in queue. You can also submit questions via Twitter by using the hashtag GPSWorldWebinar. Questions that were submitted during registration have already gone to our panelists and may be covered in this webinar. Some questions may also be answered in an upcoming issue of GPS World Magazine or in one of our many e-newsletters. We strive to answer as many of your questions as possible. If you experience any technical difficulties during today's event, use the same Q&A box at the bottom left to tell us about your issue, and click Submit, and assistant producer Jackie Petrie or I will personally assist you. Finally, a recording of this webinar will be available tomorrow afternoon at gpsworld.com/webinars. You can get to that page now and bookmark it by clicking on the header at the top of your screen above your slides. A link to the on-demand recording will also be emailed to you when it is available. Now I'd like to turn today's event over to our moderator, GPS World Contributing Editor, Eric Gaxeter.
Hey, thanks a lot, Bethany, and great to have you all here today. I think this is going to be a really interesting webinar. I haven't done one in a while, and this is a really interesting subject that lots of people are asking about. So, got a couple of highly qualified speakers today: Rodrigo Leandro from Hemisphere, and then Sunil Bisnath, a professor from the Northeast, and I'll get into his bio here in a second. So, just as a introduction, I am contributing editor to GPS World Magazine and editor at Geospatial Solutions. I've been a consultant to government agencies and private companies on GPS technology for the last 25 years. Lots of experience in the field and writing about this and covering the kind of subject that our speakers today are talking about. So Rodrigo is Director of Engineering at Hemisphere GNSS, author of numerous scientific publications and patents. Got a PhD in spatial geodesy from the University of New Brunswick in Canada. We've also very happy to have Sunil Bisnath, the PhD Associate Professor at York University, researcher in precise GNSS positioning and navigational algorithms and applications, with a doctorate in geodesy and geomatics engineering from University of New Brunswick in Canada. I think UNB is where our own contributing editor Richard is from, I believe. So great there. So I'm going to pass this on off to I think to Sunil to start off after the outline here. So here's the subject we'll cover today. One is the challenges of single receiver positioning, in other words, autonomous positioning. And we'll discuss a little bit about relative positioning with different correction technologies, the correction services technology, and then specifically PPP, real-time PPP, and then technology examples, which is Hemisphere's new Atlas correction service, and then a little about future trends here. So should be a great subject. We'll get lots of questions. We got lots of pre-webinar questions, and I'm sure we'll get some live ones too that we'll get to also. So I'm going to go ahead and push the next slide out and hand off to Sunil.
Thanks very much, Eric. Hi, everyone. We wanted to start today's webinar off with a little introduction of single receiver positioning or point positioning. There are many of you out there who know an awful lot about these things, but we do want to speak to the entire audience. So just very quickly, a few slides of the challenges related to single receiver positioning. And in this first slide, ideally, what we have is a GNSS data processing model that would assume a perfect line of sight measurement of time or equivalently distance between the satellite and the receiving antennas. However, we know that that's not the case. One of the large areas that we deal with are satellite positioning errors. The satellites broadcast through their messages as satellite positions, which are in error with respect to the actual satellite coordinates by 1 or 2 meters or so. We have a similar situation with the transmitted satellite clock correction that is that converted from time to distance represents another 1 or 2 meter of error in the position, as you can see in the figure here, projected to the user. On top of those satellite-specific errors, we also have transmission-related errors. The first being the transmission of the signal through the ionosphere. The ionosphere refracts the signal, producing many tens of meters, up to many tens of meters of error, and this error is frequency dependent. If we travel down with the signal to the Earth's surface, we go through the neutral atmosphere, or as we tend to call it, the troposphere, where we see another type of refraction that causes meter-level errors in that range as well. And in this cartoon figure, you can just see how that idealized straight line signal now has all these bends and curves in it. And again, of course, it's a cartoon. Finally, these effects, I should say, are compounded by the geometry of the many satellites that we need to track in order to produce a user position or to determine our time. So this geometry-dependent aspect, given that we're tracking many satellites. So if we combine these together in a single figure, which people are typically looking for, is what the magnitude of each effect is, how we mitigate them, and we can see that in the third column, whether we're modeling or filtering or not doing anything at all to them, and the resulting effect after any mitigation strategy. We can see that this table in another form in these cartoons, in this figure, where each block represents part of the overall observation error budget. And so we have the troposphere down at the bottom on the left, in blue, the ionosphere in the yellow block, the orbit and clock errors in the red block, and then the code and phase measurements from our GNSS, where the code measurement precision is much lower than the phase measurement precision. The typical single receiver positioning mode has mitigation strategies for the atmospheric errors, and the result is what we see on the right, past the equal sign, where we see this 1 to 10 meter level ranging accuracy that then is projected, given the geometry of the satellites we're tracking, into the quality of our user solution. So that's the situation we have in point positioning. I'll pass things over to Rodrigo, who will take us very quickly through the relative positioning scenario.
Thank you, Sunil. Hello, everyone. Thank you for coming to this webinar. So I'll start talking a little bit about how the situation changes when we look at the relative positioning case. So I will start more or less with a slide that's very similar to what Sunil just showed to you. The first thing that's important to notice here is that the fundamental effects are basically the same. If you look at the user receiver, what the user receiver experiences is the same if you are operating either autonomous or single receiver mode, as we're calling it, or in relative. The big difference here is what you do in order to mitigate those effects. In case of relative, instead of trying to model those effects, which is mostly what we're trying to do in autonomous, we either model them or filter the data in case of the code measurements, we place another receiver, which we typically call the reference receiver, very close by our user. And the whole idea here is that as far as those two receivers are close to each other enough, the effects that are experienced in the signal for both the end user and by the reference are very, very similar. which means that if we difference or if we subtract one signal from the other, those effects are mostly eliminated. So one important thing to note here is that it's a very effective way to eliminate or mitigate most of those effects, but it is a big trade-off, which is the fact that we have to have another receiver close by to operate. And we typically we require to have an infrastructure around you, and not only in terms of having a receiver that's positioned nearby your user, but also a communication in case you're operating real-time operation. So
in terms of nearby, could you expand on that a bit? I mean, it could be anywhere from what can be within a kilometer or out to how far, what kind of distance?
So this varies a lot with respect to the application. So sometimes we are referring to short single base lines. You have a single receiver that might be from a few meters to a few kilometers, and this basically gives you almost a full elimination of all those effects. So we end up with a resulting observation that is precise down to millimeters to centimeters. As you start to move away from your user, then you start to experience more differences, especially as far as the troposphere and ionosphere goes, and then end up a little bit more error. So, and then we end up with residual errors that might go in the order of several centimeters, depending on distance plus activity on the ionosphere and troposphere. So one of the ways that one of the techniques that exists to countermeasure that is to use network of reference stations, which we typically call network RTK type of applications, and then you can further model the atmosphere a little bit more, and then reduce again those residual effects. So depending on the type of infrastructure, distance, and type of atmospheric conditions, then the residual effect can vary all the way from centimeter level to several centimeters. In case of network RTK, typically you'll be talking about several tens of kilometers distances between reference stations. For when people start to talk about applications where you have long baselines up to 100 kilometers or so, that's when you end up really be talking about the decimeter residual errors in certain cases. So this is a table similar to what we had before. As I said before, the fundamental errors are the same as in the case of the single receiver. The big difference is the third column here, that we are, instead of having a mitigation model or technique, we're basically simply differencing the two observations of reference and rover. And then we end up with a few millimeters to centimeters, depending on the distance. In this case, if you're talking about at centimeter level, it's a fairly short distance or a fairly not too sparse network RTK system. And if you use your phase measurement, then we end up with an observation that's good down to just a centimeter or so, which gives you what we have today in terms of RTK performance. Not only gives you a very accurate phase measurement, it also gives a very good notion about the atmosphere, which helps you to initialize a receiver very quickly. As we have today, state-of-the-art RTK systems, they are able to reach centimeter level in just a few seconds. So this is the graphical visualization of the same table as we had before, where we have all the errors again, same for troposphere, ionosphere, orbit, and clock. And then on top of those, we have a little bit of what the phase and code measurement noise adds on top of that. When we subtract the reference data, most of the systematic effects, which are the troposphere, ionosphere, and clocks, they are removed. And the code and phase measurement noise is a little bit increased because these are stochastic type of errors, and then they are added up instead of being subtracted because they're not the same at reference and rover. But at the end of the process, we end up with code measurements that are good to a few meters, and phase measurements that are can be modeled down to a few centimeters, and this is what we end up using for RTK systems to have centimeter level positioning with very high reliability and robustness. So that's basically how we end up with what we call today RTK level of accuracy. So if we investigate a little bit how things fit in terms of when we compare to single receiver application that Sunil talked about with a relative, if we put them on a chart where we have the accuracy performance, where we have the relative position is the most, or the highest level of performance you can get, single receiver is the lowest, and in terms of availability, single receiver is the most available because it's available anywhere on the planet, while relative will have to rely on infrastructure or nearby infrastructure, then is the least available system that you have. This is more or less they fit in that chart. Between them, what we placed here was a compromise region where we can move between the two, and we can make compromises in terms of how much infrastructure you have around you and how much accuracy or how much performance you want to achieve. So just to give some light on what that could look like, and we can debate where those type of systems go inside this chart. There's always a discussion about that, but we thought, okay, SBAS would go more or less in the middle of the two, because you have then a system that's available for whole countries or very, very, very large regions, but you have still a big compromise in performance when you compare them to network RTK systems. They are still sub-meter level systems. And then we have network RTK. Again, fundamentally, they are very similar to fundamental single receiver relative positioning, but they still require a lot of infrastructure. Even though you can increase a little bit the coverage area of those systems, it's still very small when you put this in comparison to what you can achieve with a single receiver on a worldwide basis. So that's why it's so close to what we call in the relative. But yet it's very, very close in terms of to the best we can do in terms of accuracy. So on top of that, what we would like to see is, okay, where we want to be, right? Where we want to be in terms of GNSS industry or scientific community, what we want to, where we want to get at, which is basically the very high corner, the corner on the right high right side. And that's kind of the holy grail of GNSS performance. We're not there yet, and all the work both the industry and scientific community has been doing is trying to find ways from some direction on how to get to that point eventually. Today we talk a lot about correction services, basically global correction services, which is one way to try to make the single receiver case to migrate in terms of accuracy. We're placing this error coming from the single receiver because of the global nature of correction services. These are services that are available worldwide, so they fulfill the availability requirement in terms of being available all over the planet. Now, what the correction services do, they are bringing more accuracy to that availability, and that's why we are moving upwards from a single receiver, and that's what we're going to be discussing a little bit more in the next slides, how this is possible, how that works, and give you some examples. I'm going to pass over back to Sunil, and he'll be talking a little bit about how global correction services work in general.
Yeah, if I can just interject just for a minute, just so for RTK networks, for example, and at least here in the U.S., probably about 35 different states have set up their own statewide RTK networks, so you can access RTK from that perspective. But again, they're all regional services, whereas when Rodrigo talked about global correction services, that means you can use it anywhere in the U.S., anywhere in North America, South America, Africa, Asia, Europe, and so on, without in a very consistent manner, rather than having these regional systems. So RTK networks are a small regional. SBAS, like WAS in America, is sort of a nationwide system, and the global correction services are just what it says. It's absolutely global.
Thanks, Eric and Rodrigo. So just a few slides on generally what's meant by these global correction services. It's important to talk about them at least a little bit to understand their characteristics, because the average user never actually sees or touches the infrastructure that's involved. First of all, in this figure we have basically if we go through the chain here at the top left, it's all based on a global network of reference stations, GPS or GNSS reference stations around the globe, and we can always go into quite a scientific debate on the number of stations that are necessary, but the global coverage is what's key to be able to continuously track the GNSS network or satellites or constellations that we're interested in. With that backbone or that infrastructure, we then collect all of this tracking information, which is the same type of information that a user is tracking, the code and phase measurements and broadcast messages from the satellites, which is all then brought together at a processing center where all the data is processed. The results of that large estimation process is satellite information, orbit and clock information, very precise orbit and clock information. If we go back to the single receiver positioning error budget, we can then really bring down the orbit and clock errors in that part of the budget. On top of that, we can also estimate other corrections such as atmospheric models and other satellite biases. This so-called satellite correction data, these are then transmitted to the end user via satellite or the internet, depending on the particular system. And at the end user system, the user has their GNSS unit with firmware that does the end user processing and also receives these so-called satellite corrections or the correction data that is then combined with very specialized algorithms, including the processing of the carrier phase measurements and other models to produce the user position that we know. We should also mention that within this process of making use of the carrier phase measurements, the carrier phase measurements, as most of us know, contain an unknown component, an unknown number of carrier cycles for each satellite, known as the carrier phase ambiguity. And given that we're doing this processing through the ionospheric refraction we talked about, this requires time to get the proper estimates of these carrier cycle counts for each satellite. What that means is that when these global solutions are run at the user site, there tends to be a period of convergence required in the solution from when the receiver first starts operating before we reach the few centimeter accuracy level, the so-called convergence period. And this is typically on the order of minutes or perhaps a few tens of minutes. And that's why users have this convergence period. And the result has been that these systems have flourished in certain areas, such as offshore farming areas, large open space areas where the network, for example, network RTK infrastructure hasn't existed. The correction services have become the de facto standard in many of these applications. So with that general description, I'd like to pass things back to Rodrigo, and he'll give us a very specific example and go into a number of more details.
Thank you, Sunil. So I'd like to talk a little bit more now about an example we have here, which is the Atlas Correction Service. This is a correction service that Hemisphere introduced about a few weeks ago. And the first question that you might be asking is why should Hemisphere introduce a new correction service? So, because as we know, there are already services out there. So what's the problem we are solving here by introducing a new one? So first of all, Hemisphere, as we just showed to you, this is one of the trends in technology moving forward. So this is how we want to see GNSS technology moving forward in the future: global availability, very high accuracy, very spread usage of high accuracy technology everywhere. So that's what this is part of. Hemisphere needs to have something that's part of their product line as part of their of our products. This is one side of things. The other side of things is that there is still, this is a fairly new technology still. There's still much ground to be covered, as we're going to be discussing the future trends section. And also, there is still largely unattended markets that are still not making use of this type of technology that could be attended. And this is one of the problems we are focusing on, which is to making sure that this technology is actually available to people or businesses that didn't have access to that before that. So we have cases where sometimes OEM integrators, they either don't have an option to introduce this technology in their products, or they have too restrictive options to introduce that technology in their products. And that what we want to do is to offer a cost-effective, business-effective option for those businesses and people. And one of the things that I would like to say is we created Atlas to be a service where Hemisphere is also, as you very well know, a hardware provider. But our mentality is that we use our hardware so that we can offer this service in a wider basis, instead of using the service so we can sell more of our hardware. So our mentality is we want to make sure that the correction services are as available as possible to people who either didn't have option before or have too many restrictions to have that type of technology. In terms of the system architecture, it is very similar to the general description Sunil just gave to you, which means that we have infrastructure where we get network reference station data into control centers. These control centers, they process the data, they generate precise information about the satellites. This information is encoded in a proprietary format that we created, and this is also one of the key things about the Atlas service. We have designed a very state-of-the-art, future-looking message design for this system. So we believe that we are prepared to contemplate applications for the next several tens of years with the message we designed. These messages then either send over internet to our users. These are the users that connect to the system over internet, or they go through an uplink facility, transmitted to an L-band satellite, and then transmitted back to the users over L-band. These are the users that are receiving the corrections over satellite transmission. On top of that, in our architecture, we have a customer portal, so the users can go access a system over the internet, make their purchases, configure the system. So it's part of the business side of things, where we try to make the system as easy to use and configure and manage as possible.
Can I ask a quick question, Rodrigo? And I hope you can just touch this a little bit. So the difference between RTK and this type of services, and I think an example here is, for example, Washington State has an RTK network, and they use upwards of 100 reference stations just for the state of Washington. For this type of architecture, what's the density of reference stations, would you say?
So typically, the systems that run this type of technique, they run with a global network of anywhere between 100 and 200 stations distributed worldwide. And after that, depending on the type of correction system you are providing, then that's pretty much all you need. If you are dealing with further modeling of ionosphere or atmosphere in general, then start to migrate kind of somewhere between network RTK and global correction services. But to reach the performances that we're looking here, basically the user don't need to care at all about what's around him. He just needs to connect to the system, receive the corrections, and he gets the performance basically everywhere, independent of the infrastructure. In terms of coverage, this is a very standard L-band type of coverage where we go up north and south somewhere between 70 and 75 degrees. When you look at the internet coverage, it's basically restricted only by where you can get internet connectivity, and then as long as you can connect to the system over internet, then you can use it. There is no limitations there besides the connectivity then. So this is a little bit a closer look on how the performance of the system looks like, and now we're bringing to you a practical example of what I've been talking about, that where we're saying, well, you can actually reach centimeter level with a single receiver, which is what we're showing here. And as part of the compromises of running a global service and being available everywhere with today's technology, we have a little bit of a convergence time, which is what you can see in the lower left plot. We have a few minutes of convergence time, but eventually get down to a sub-decimeter performance. And if you're running on a receiver that has reasonably good environment, then end up with not more than 4 centimeter RMS and so on, which is very sufficient for a wide number of our practical applications. So you can think of how many applications can be served with that level of precision when you think that, well, and I don't need to care about connectivity, or if I'm inside the network RTK system, or if I'm in a country like Brazil where I don't have access to S-Bass, and this kind of performance is actually available. As a matter of fact, one of the things we were discussing just earlier today is that this is what we call the H10 service, where we offer the sub-decimeter performance. And we offer 2 other levels of service, and one of them is we call the H100, which is meant to be some sort of S-Bass replacement for people who either don't have access to S-Bass or would be interested in having an S-Bass type of performance where we have not only GPS available as part of the system, but also GLONASS and so on. So these are also the other levels of service we also offer as part of the system. So this is still looking at the high accuracy level service. As you can see, it's just 2 different ways to look at how the performance looks like. On the left, we have the height performance. Again, given the time, it goes down to a few centimeters and so on. And on the right-hand side, we have the plot of the scatter plot of the horizontal position error, which is again very well contained within a decimeter box. And again, this is very sufficient for a very number of applications. And the whole deal for the Atlas system is that what we're targeting to is to talk to people and make sure that they understand that this technology exists, and that there is a business that is really willing to make sure that they have access to that. And that's what we are working on right now as part of this system.
Rodrigo, just a quick question from the audience that I think is good to cover right now. The audience is asking which constellations are supported by the Atlas architecture.
So right now we fully support GPS and GLONASS, and we have partial support to Beidou, but we will have full support to Beidou very soon. That's the current situation. So right now, so this slide I'm showing a little bit of different view of how you can look at the performance. This is what we call pass-to-pass. Just to give you some background, this is something that's very typical in agricultural applications. In agriculture, people typically are concerned about how well we can measure the distance between two tractor tracks, and those tracks are typically separated by 15 minutes in time, which is what we then define as pass-to-pass, which is your kind of a correlated error over 15 minutes time frame. And that's what we have here, what Atlas Systems is capable of providing, that type of positioning capability. About 2.5 centimeters, 1 sigma, 5.7 2 sigma. It's very typical performance we get. This is another example. It's a little bit more on the survey, kind of survey GIS side of things. That was a test we did to verify a repeatability of a position. So what we did was to use a receiver to observe a point, and that's where you can see in the red box the convergence, where we are basically waiting for the system to converge on top of a point, and then we walk around under trees and so on and came back to the same point afterwards. What you can see in the yellow box is the time where we are moving around under the trees of the receiver, and then on the two green boxes are the times when we were observing the point before moving and then observing the point after movement. Coming back, and you can see that's pretty consistent, and that's what kind of performance we have been consistently seeing when we perform this type of observations. So these last slides we've been talking about how the technology looks like and how the performance what kind of performance can be expected and so on. But then the other big question is how you reach the user, how the user gets access to the system, how you reach the market. And of course, Atlas is being introduced as part of a Hemisphere line of products, but we also created a new smart antenna, which was especially created just to support the Atlas service. So we are calling this smart antenna, the Atlas Link. It's a multi-purpose smart antenna. It has a lot of capability, including internal memory, web server, Wi-Fi connectivity, and so on, and a few other very interesting features. As I said before, one of the things about Atlas is that we want to make sure that the people really have access to L-band services. And the Atlas Link antenna has one of the features that allows us to make that to happen in certain cases. That feature, one of those features we call the Smart Link. And this is one of the solutions we created to expand the reach of L-band services to people who would otherwise not have access to that. So what you see right now is the situation for a user that has a GNSS device with no L-band capability, and for whatever reason, either technical or cost or whatever reason it is that the user doesn't have access to that, what we have is, well, L-band is transmitting signal, I have a GPS receiver or GNSS receiver, I can track my satellites, but the best I can do is to create a position solution that's what we might be calling the single receiver or S-band solution. So how we solved that? So what we did was to create a capability inside Atlas Link where the user is able to install that antenna on the same platform or vehicle where he has his existing system, and that antenna will receive the Atlas L-band signal, and then over a connection, which could be a serial connection, it sends standard data to the other device in, say, RTCM format, and that other device is able to produce an Atlas position. So this is a solution where people would like to have to extend their capabilities, say with L-band, but don't want to touch their installation too much. So this works as a sort of L-band extension to existing installation. So people who have receivers that are maybe not able to track L-band, or maybe these are single frequency receivers, this also works fine. So that's and this is all, as I said before, this antenna has a Wi-Fi server, a web server with Wi-Fi capability. So this is all very easily configurable with a phone or any device that has Wi-Fi capabilities. Just to give an example, this is an example of a smart link in operation. What we did was to connect smart link to two different non-hemisphere receivers and run the system for a few hours. And you can see that this is basically a typical performance that, as we were showing before, the typical convergence time at the beginning, as we have discussed, is something that to be expected in global services. And then the final performance down to just a few centimeters, as we typically see. So this is a summary, very short, very high-level summary of what Atlas is, which is L-band, a correction service offered over either L-band or Internet that can provide you with position solutions at 4 centimeter RMS or so. In addition to that, with a few extra capabilities to support additional hardware, such as Smart Link and so on.
So also, I'd like to add in there, Rodrigo, maybe you could expand on it. But so they don't, the user doesn't require the Atlas link because some manufacturers, some GNSS receiver manufacturers, can embed the Atlas service within their receivers. Is that correct?
That's correct. That's part of our business model. So we are an OEM-oriented business. So whenever other manufacturers need to implement what we call the Atlas library, this can be available in other receivers as well. So I'll pass back to Sunil. He will lead us over the future trends slides, and we'll be discussing about what we expect in the future.
Okay, thanks, Rodrigo. I know, Eric, if you had any comments or questions before we move into this last section.
I think we're good. There's a few questions from the audience. Actually, one, if we can attack right now, is one question from the audience is, to reduce convergence time, can you start on a known coordinate, let's say a survey control point or something along those lines?
Yeah, well, I can. Sorry, go ahead, Rodrigo. Okay.
That's actually possible. Sunil, go ahead.
Okay. Yes, that is possible. I mean, it's a standard sort of least squares problem. So if you have known coordinates, you can much more quickly find a converged solution if you know what the solution is. So you can use the known position, set up on a known position to quickly get your ambiguities right, and then go on from there. So theoretically that's done, and people have done that kind of work. If the question was, can a particular service do that, I would have to pass it back to Rodrigo.
Well, so this is something that we still are working on for as a capability for Atlas, but as soon as you said that this is perfectly possible. This is a problem of you have a system where, as we said before, the big constraint on convergence time is resolving the ambiguities in this type of systems. And if you know your position, you can resolve that much faster, and then that's how it works.
Okay. Well, thanks, Eric. It's a good question to lead into, what's happening now, what we're going to see in the near term, and in sort of the longer term beyond the decade, and some of these sort of future trend comments are I think are very clear, and I guess as we get further in the future, things become a little more uncertain. So there are no guarantees. But what we've done here is talk about a few aspects of what is happening, what we see happening, and what we believe will happen with these global services in the next number of years. The first aspect is accuracy, which everyone's always looking for their positional performance. And what Rodrigo was showing, these few centimeter quality solutions in static or kinematic, in kinematic mode, while they are extremely good, they can be improved, and they can be improved in a number of different aspects. We've listed some of them here in terms of the ionospheric estimation, the tropospheric estimation, the pseudo-range and phase multipath and noise, ways to mitigate those, and the satellite orbits, clocks, and the other equipment delays or biases that are involved in these types of complex solutions. So those are where the error budget can be squeezed and improved. And what we have on this slide is just a few comments on each of those major areas. And what we are seeing is small but noticeable improvements in each of these areas. With the ionospheric estimation, improvements in the estimation process, improved models to provide a priori information or for single frequency processing, and there are of course a huge number of single frequency users out there. The introduction of L5 on GPS and other constellations, these multi-frequency linear combinations to make new effective frequencies that will improve ionospheric estimation. Small improvements in the tropospheric estimation, new models, new improvements that continue. Pseudo-range phase, multipath, and noise, which are always difficult, but more hardware improvements from the antenna to the receiver, the correlators in the receiver, and in the processing algorithms. So small improvements still continue, and all the way down to the satellite orbits and clocks, where there are groups that are trying to squeeze the next few millimeters out of each of these, and they do improve solutions in time. So we do see small improvements in accuracy coming along the way. Of course, a very big question, and it's always asked when we're discussing these topics, is will these types of global solutions work eventually like RTK or network RTK? And the answer to that question lies in the initial convergence period that's required to estimate the float and then the fixed ambiguities. Can that be taken down from tens of minutes or minutes to tens of seconds, which would allow the use in many other applications that have a lot of obstruction, such as construction, the use in urban areas, etc., where I think a lot of users may want to use these types of global services more frequently. There's a wide scope of potential improvements to bring convergence periods down. Multi-frequency, multi-constellation measurements, more of the brute force approach, where we apply more measurements, unique measurements to the estimation process, and that has shown significant improvement. Also, related to the convergence, the consistency, quality, the integrity, or so-called the robustness of the solution, to increase performance that way. The mitigation of the noise and multipath that we've talked before, use of other data to aid in initialization, including, Eric, the question you asked, where if we have a priori information about position as well to help. We've seen a lot of work in robust reconvergence of solutions, and robust ambiguity resolution and validations an issue. So in the next slide, just some comments on each of those. I would just make highlight a few of them. The main ones being the multi-frequency, multi-constellation availability has shown great improvement in convergence, more so than position solutions. So for example, adding GLONASS to a GPS solution does not make a great improvement in positioning solution performance, but it greatly reduces convergence. However, there is the law of diminishing returns that we have to consider, and that's that as we add additional constellations or additional measurements, for that matter, after a while they don't make that much of an improvement. So we add one constellation to one, and we see a big improvement, and adding a second, a third, a fourth, and so on, we see smaller and smaller improvements. So there's one other aspect, and we see that in some of the questions that have been asked, and we can frame it from the sort of consumer market, if we use that term. How can these global correction services be applied in the near term or over the next number of years to to the consumer market. That is, if most of this work considers dual frequency, high quality receivers with high quality antennas. What if we consider low cost receivers and antennas? Well, right away, as soon as we put in a low cost antenna, the quality of the code and phase noise deteriorates, the multipath goes up, there can be phase cycle flips, etc., and these make quite a difficult job for the processing algorithms to handle. So can there be a somewhat graceful transition to lower quality hardware? Can such correction services be used in conjunction with assisted GPS, assisted GNSS solutions, or combined with other technologies such as IMUs and other sensors? There are a lot of possibilities out there, and there's a few thoughts on this slide of some of these possibilities are quite great, and others will be very challenging. For example, making use of low-cost antennas makes it very difficult to process the data that's resulting from those antennas. So with that, and given the time, we'd just like to summarize with one final slide before passing things back over to Eric. And what we can say in a nutshell is that with more signals, these global services show performance that is getting more and more RTK-like. Also, and perhaps almost as important, is that these globally available, very general corrections from these sources are being generated now in a very consistent way to provide few centimeter or centimeter level single user positioning and navigation in a global basis. And one would expect that as we move forward with improved technology, lower cost, and multi-sensor systems, that we'll see continued increase in the precision of the overall solutions. So with that, I'd like to pass things back to Eric.
Thanks, Sunil. So we got some great questions here, and I think one that was actually covered in one of the slides, but maybe we need to emphasize it, and this is for Rodrigo. And the question is, will third-party receivers require firmware enhancements and able to use Atlas Link?
Well, to use the Atlas Link, no. If you are talking about what we discussed in terms of the Smart Link feature, where you just plug in Atlas Link to an existing receiver, any RTK capable receiver that supports a standard correction message such as RTCM would work with absolutely no modification.
Right,
it's
so
really
it's just an RTCM output from Atlas Link.
Yeah, so it's really a 15-minute process to get it up and running.
Okay, very good. So more or less plug and play, just to output RTCM out of Atlas Link and then plug into your receiver. And virtually all dual frequency receivers these days are RTCM3 compatible.
That's correct. So it is designed so that the other receiver understands what's being transmitted in the messages. So.
Okay, so another question is, the audience asked, you talk a lot about accuracy, but what reference or truth are you using? So I guess probably the question is, which datum is Atlas referenced to?
So it's ITIF 2008, which is a very typical, it's kind of a high accuracy version of WGS, if you will. So this is kind of a industry or scientific standard for global reference frames nowadays. So that's what Atlas uses as well. Most of the systems use a similar reference system.
Right. That's been my experience too. I think it's the current date epoch too, right? Or within within a half a year or so. Okay.
Yeah.
So we talked a bit about, Sunil talked a bit about the advantage of multi-GNSS and how you have diminishing returns as you add constellations. One of the audience members is asking about triple frequency. So if and when you bring L5 into the solution, is there any advantage there for accuracy or convergence time?
Yes, clearly there's a couple of aspects. If we just, for example, consider just GPS L1 and L2 versus L1, L2, and 5, not considering other constellations, but just using the one example of dual to triple frequency, there's a few areas. One is with just various linear combinations of those three frequencies versus two, you have additional data, and that increases your power to estimate your solution. So we can see an improvement in initial position estimate. So then that reduces the convergence time because the initial estimates are more accurate than they were with just dual frequency. We also can, through a lot of work that many people have already done, trying to find the idealized combinations for better handling the ionosphere, better managing it. And so we also see improvement there, significant improvement, since the ionospheric refraction is a significant limiter to quick estimation of good float ambiguities to get us to fixed solutions. So that also helps. And then that becomes quite significant to the point that in some simulations that have done, some researchers report very, very quick convergence, down from the tens of minutes and minutes into the tens of seconds range in simulations under idealized conditions. So there's great hope for the triple frequency solutions.
And I'll add on top of that, on top of that, some of the new third frequency signals we are seeing, like B3, we have a better quality of the code measurements that we can make out of those signals. That also helps. So in addition to all the work that we can do on ionosphere linear combination, sometimes in certain cases we're actually seeing better signals coming up, and those also help with convergence and general performance.
So along those lines, one of the audience members is asking about L2C, and I guess that's a question I would have too. Is, are you taking advantage of L2C with Atlas, or do you see yourself, if not, are you see yourself taking advantage of it down the line, and does it really add to the performance of this service?
So the L2C helps in terms of it's a signal that you can track the signal more robustly, right? You can track L2C in certain situations where otherwise not being able to track L2E. So in terms of having more positions available, yes, that would help. In terms of final accuracy and convergence, I don't think that would make much of a difference as compared to our existing L2P signals that we use for GPS.
Okay. And so another question, this is one I had too, and I think it's worthy of some clarification. And one of the audience member asks, what's the difference between SBAS, and I think he's referring to either WAS or EGNOS or MSAS or GIGAN, those type of systems, the single frequency sort of sub-meter systems. What's the difference between that and PPP, like the Atlas service, for single frequency receivers?
So you want to do that one or do that one?
Sure. I can speak just generally, and if you want to follow up with Atlas specifically.
Okay.
I mean, there are differences between something like WAS and let's say PPP algorithms, in that there are similarities and differences. I mean, the similarities are with WAS, there is a network, or if we're talking GIGAN or EGNOS, a regional network that is providing improved orbits and clocks and atmospheric models that are being then transmitted and applied as corrections by the user. However, at the user end, these are typically L1 code corrections. There might be some code smoothing, other things that are going on. Whereas a PPP solution is more sophisticated. It's making great use of the phase measurement and the filtering. So the WAS type solutions are more similar to what was referred to as autonomous positioning or point positioning, where what those systems are doing is they're not providing necessarily greater accuracy. They tend to, but their real focus is on integrity, providing availability and integrity for safety of life applications, specifically civilian aviation. Whereas PPP tends to refer to dual frequency solutions, and they're provided with much more sophisticated processing algorithms that allow for after convergence the few centimeter type kinematic solutions that Rodrigo has shown. So there are one can say that they're for different markets in that sense. I don't know, Rodrigo, if you want to follow up.
No, it's fine for me.
So I'd like to sort of lead into the conversation about the different levels of service. I think Rodrigo addressed that a little bit earlier, but I'd like to make it clear. So there's, as far as I understand it, and I'll sort of summarize, and Rodrigo, maybe you can respond, is so there's the H10 service, which is sort of the traditional dual frequency PPP service that gets you down to a few centimeters accuracy with some convergence time. And so there's an H10 service from Atlas, and there's also an H30 service, which is a sub-foot solution. And I don't know much about that service, and maybe you can expand on it a little bit. And there's the H100 service, which is a sub-meter service. And I guess to expand on the earlier question, the difference between a system like WAS and Atlas on the single frequency level is that WAS is a GPS-only system. I don't recall if EGNOS is either. It might be dual. It might be GPS GLONASS, but certainly WAS is a GPS-only service, whereas Atlas, I believe, on the H100 single frequency service for sub-meter accuracy, is a GPS and GLONASS service. And where that can become important is not necessarily in open environments like in agriculture and such, but when you start working in environments where under tree canopy and in difficult environments where you need extra satellites, for example, GLONASS, and you can get direct corrections from Atlas for both GPS and GLONASS, there can be a distinct advantage there. And I'll pass it on to you, Rodrigo, for your comments.
Yeah, absolutely. So it's both the matter of having multi-constellation support and also the geographic availability, right? Because then there are regions of the world that you have absolutely no access to S-bus systems. And yet those regions, they still have applications that could benefit from those type of levels of accuracy. So coming down to the H30, it's basically the same thing about how you make your compromises in terms of cost and accuracy. So certain people don't need as much accuracy, and they would be willing to buy a service that's not as accurate but at a lower cost, and that's where the different levels of a service come from. To have H10, which is basically ultimate accuracy that you can get with a global system today, and then have H30, which is a compromise. We still need some kind of a sub-foot accuracy, maybe for MGIS application and our agriculture application, but they don't need a centimeter. And then have H100 that basically covers typical user cases where you would be happy with access to a multi-GNSS S-bus type of system, type of performance.
Okay, thanks for that. So another really good question from the audience is they ask about the applicability of Atlas in dynamic applications, for example, moving vehicles. And so they're asking, can the solution reconverge if GPS or GNSS is temporarily lost in a dynamic environment? And I assume that the audience member is speaking of passing under a bridge or that kind of scenario. But I think in general, talking about the dynamic nature, because people may be thinking this is only for a static solution, but I think we need to talk about using it on tractors and other dynamic applications. So can you speak to the performance in that kind of environment, Rodrigo?
No, absolutely. So when you look at how the data is processed, how things are implemented in the GNSS processing side of things, there are no assumptions about the receiver not moving. So all the assumptions that are made when we compute a position are made, we're assuming that the receiver is moving all the time. And therefore, basically, besides changes in environment, if you're under a tree or going on a tree or in the open, if you're moving or not makes no difference. As a matter of fact, hemisphere receivers, they are able to operate at a very high dynamic environment. We have seen that in the past. So this is something that we support in general.
Okay, and then another question is, and actually it's from several people, and we've sort of addressed it during the webinar here, but maybe we can touch on it again, is a lot of people are asking, hey, is worldwide PPP, does it have the potential to replace local RTK networks in the future and offer global coverage? And I know we've touched on it a bit in the earlier part of the webinar, but I think it's such a key point we ought to have a short discussion here about it too. Maybe Sunil, you can start on that.
Yeah, maybe as the academic, I could be a little more free with my words than Rodrigo. But that's that. We never want to say never. But at the same time, we've seen this fairly steady progress, as we described in the webinar. Steady progress in improved performance and reduced convergence period in these global solutions. And we've also seen when we've added constellations and we've taken into account the issues between constellations, whether they're spatial datum or temporal datum differences, interfrequency, interchannel, interconstellation biases. There's a lot of work that needs to be done to properly integrate different constellations. But when we do, and the measurements then become sort of generic additional measurements to the solution, one needs to understand that these solutions are measurement driven. So the quality and the quantity and the availability of the measurements really absolutely drives the quality of the solution. So we are improving those solutions, and I could stick my neck out and say that yes, I think we will see near RTK-like performance with these global services. I mean, that's the sort of the holy grail, the goal, and as we've seen in simulations, other things, we see some quite good performance. It won't be tomorrow. It'll be maybe a number of years away still, but we are seeing significant improvements. Now, that does not necessarily mean that we'll see the disappearance of RTK networks and other things like that. I mean, the systems do work differently, and they perform differently under different conditions. So I'd have to include that caveat. But we're making great strides.
Rodrigo, would you like to comment?
So yeah, no, but I don't disagree at all from Sunil, right? Like I believe also that that's the way we're going. That's where we're going to eventually get. There are a major number of people in the GNSS community, both scientific and industry, working towards that, and that's where we want to be. I think there'll be different aspects on how we're going to get there. Parts of improvement will be on the constellation. We are going to have more satellites and more frequencies. We're going to have more data and better data that will help us to improve and start to move in that direction. We're going to have more things going on in the infrastructure also that will help, and also in algorithms. So how well we understand the Earth and atmosphere, and how well we can model those effects also play a role as well. So when we put all three together, the progressing over time, and a number of people working on those, then we are going to move towards that direction as we move on. And I really believe that eventually we're going to get there. Now, I think that over the next years, what we're going to see is people will come up with a very interesting concepts on how to make compromises across those three areas of improvement in terms of giving you a little bit of an edge in terms of performance in certain situations, either with more infrastructure, or if with more innovative ideas, or with more signals and satellites. So I think that will be a long transition phase and a very interesting one, where we're going to see a lot of interesting concepts coming up over the next years in both scientific and industry. scientific community and industry, and that's what I believe that we're going to be seeing over the next year or so, and eventually I believe we're going to get there, yes.
Yeah, and just a thought from my perspective is that it seems like you could also come up with a sort of hybrid RTK PPP solution if you had a more dense network of reference stations that you could access within certain regions, right? Then you could sort of enhance your PPP solution and sort of get a hybrid or even near RTK solution. Is that correct?
Absolutely.
Well, very good. Well, we've gone 10 minutes over since it's been such a lively conversation here and lots of audience interaction. There's still lots of questions left, but we've sort of reached our limit here. So the contact info is on the slide right now for myself, Rodrigo, and Sunil. And it's a great conversation, guys. I really appreciate it. And Bethany, it's back to you now.
Thanks, Eric. And thank you to our audience for attending today's webinar. If you have any more questions, do not hesitate to contact our presenters at the emails on your screen now. Links to their email addresses are also in the bios at the left. An on-demand recording of today's webinar will be emailed to you tomorrow afternoon and will be available online for a full year at gpsworld.com/webinars. If you'd like to share this webinar with your colleagues, you can do so via any of the links on the left-hand side of your screen. You can also download today's slides by clicking on the green folder icon at the far right of your dock. If you aren't already a GPS World Magazine subscriber, we'd like to invite you to sign up today for free. All you have to do is click on the GPS logo at the far left of your dock and fill out a short form. Our next webinar is scheduled for Thursday, August 20th at 1 p.m. Eastern, 10 a.m. Pacific Time. Registration will be opening soon, so check back at gpsworld.com/webinars. We look forward to seeing you at a future webinar.